Hello everyone, welcome again to this YouTube video. We have been talking about the recursion, and in today's session we'll try to solve few good quality questions on the recursion so that you have a good confidence on that, and then we'll move to the next one. So in the last session, in the last video which we did on the YouTube, we talked about Tower of Hanoi. We'll just begin the problem statement, and then I'm expecting that you would have already solved, or if not, just try to solve the problem with me, right? The question I'm again repeating. So the problem statement says that there are three different tables, right? Let's say this is the source table, this is the destination table, and the third table, which is a help called as an auxiliary table. And on the first table, which is the source table, let's say that there are n number of coins. There are n number of coins lying on the first table. These are the n number of coins. And how these coins are arranged? The coins are arranged with a specific order. Only the smaller can go over bigger coin. It means that in no way it's possible to go and store a bigger coin over a smaller coin. So smaller has to sit over the bigger coin. That's number one. And ultimately my task is that this entire list of the coins, this has to be moved and brought into the destination. But again the condition is only one coin can be moved at a time. So the question says that how many steps does it take? How many steps does it take to move all the coins? How many steps does it take to move all the coins from the source to the destination? Right? Let's try to understand with the help of an example. Let's say that I have a scenario case 1. The case 1, let's say that I have only one coin on the source. Right? I have only one coin on the source. This is destination, this is auxiliary. So in this case, if I have to move the one coin from the source to the destination, what I'll do, I'll try to go and move this coin from the source to the destination. In how many steps it will happen? It will happen in the case of, it will take just 1 steps to achieve this. Let's take the another case. Let's say that's case number 2. In the case number 2, again I have a source, I have a destination, and I have an auxiliary, right? And on this I have 2 coins. Now if I have to move 2 coins, I have a condition that at the go I can only move 1 coin. So what I can do, I can take this smaller coin from here till the auxiliary. So this will take 1 step. So when this step happened, how the situation will look like? This is my source, this is my destination, this is my auxiliary, and at this moment of time, auxiliary had this smaller one and source has the bigger one. Now what I can again do is that I can move this to the destination. So this is the second step. So when the second step happened, typically what does that look like? It's source, destination, auxiliary, and then you have this bigger coin here and the smaller coin here. What you can do again now is that you can move this coin here to here. So this is the third step. And when this step also happens, finally, this looks something like this: source, destination, auxiliary, and on the destination you have the bigger coin that looks something like this. Fair enough? So if you see here, to move the 2 coins, I have to take 3 steps. So the question is, if I have n coins, how do I go and solve it? Now as the number of coins becomes more, solving it humanly becomes very complicated, very tough, and that's where we'll go and make use of recursion. Now when I was starting, I told you, whenever you're trying to solve a recursive function, let's try to do a quick revision. In the recursive function, you always have to deal with 3 things, right? You have to write a base condition. Then you have to write the logic, and then you have to write the recursive call. These are 3 important parts of any recursive function. But apart from these 3 points which you see here, right? Apart from these 3 points that you see here, there is one more key thing about the recursion. So the real thing which can actually help you solve the problem very effectively is that if you're able to make a right function definition or signature, right? What does that mean is that how many parameters the function should have, what should be those parameters. We should always make sure that you define a recursive function in such a way so that all the information which has been given typically in the function, in the question, you are able to effectively go and use it. If you are able to well define a function, trust me, half of the work is already done. Right. Another important aspect about the recursion is that normally when you go and define a good definition of function, when you go and define this is defined, you have to, your half of the work is done typically, right? Typically making use of this function, you can go and call and break the problems in a smaller way. So let's try to understand with the help of this example, right? So let's say that in this example I have a information. What are the information that is given to me? The informations which are given to me are 1a, which is the number of coins, right, which is n, right? This is one information that is given to me, and the other information given me is that 3 tables. There is a source, there is a destination, and there is an auxiliary. You have to move the things from the source to destination using the auxiliary. So using all these information, if I have to go and define a function definition, how does that look like? Let's say that it looks like something like this. I go and say that the name of the function is moves, which takes n coins, which moves from S to destination to auxiliary. Let's say that assume that this is a moves functions which knows that if you give n coins, it will tell you how many moves does it take to move n coins from S to D using A. What does it say? Number of moves required to move n coins from S to D using A. We assume that moves is a function. Let's not worry about the logic right now. Just think that this moves is a function, which if we provide n as a number of coins and we go and say that S is the starting, D is the destination, A is the auxiliary, it will help you tell that how many moves it will take to move n coins from S to D to A. Now let's suppose if that is a function, I have defined this moves n coins from source to destination using the auxiliary. If that is the case, if I go and define this function like this, moves n minus 1 source destination auxiliary. Can you guys tell me what will this mean? If this is a function that I believe in and I've changed the parameter, the meaning of this will be that the number of steps needed to move n minus 1 coins from S to D using A. Am I clear? That should be equal to the number of steps needed to move n minus 1 coins from S to D using A. Right? Similarly, if I go and change this, let me go and call it as moves n minus 1 S, A and D. If I go and change this, what will the meaning of this? The meaning of this will be, you can just pause the video and put that into the comments. It means that the number of moves needed or number of steps needed to move n minus 1 coins from S to A using D. It will tell me from S to A using D. Number of steps needed to move n minus 1 coins from S to A using D. Now let's assume that if this is the function that is available to me, I'll write the logic later on. Let's try to go and apply the problem here. So let's say that I have a problem something like this. Let's say this is a table source, destination, and this is auxiliary. And right now I have n number of here, right? This is the n number of coins here. Now if I have to move this n number of coins, let's try to break this problem. Let's try to break this problem into the problem of n minus 1 coins. Let's say this is n minus 1 coin. So first of all, if I can go and move this n minus coin somewhere from here to here, for this let's try to go and make use of a step called as moves n minus 1 coin from source to the auxiliary using destination, and this is equals to n1, that is number 1 moves. If I go and do this, this is how the situation looks like. I have source, I have destination, I have auxiliary. On the source I have the bigger coin, on auxiliary I have the smaller number of coins. So these are n minus 1 coins, correct? Now what I have to do, I can just go and move this coin from here to here. It will take one step. When this happens, the situation looks something like this. So I have S, I have D, I have A, and this bigger coin is on the center one, and this has n minus 1 coins. Now again, if I have to go and move this n minus coin here, I can go and again make use n2 steps will be equals to moves n minus 1 coin from A to D using S, which will finally bring the situation like this, where all of the things are at the right position: source, destination, auxiliary, and then I have this bigger coin like this, and this is n number of coins. So the total number of steps, if I have to go and find what will be the total number of steps, the total number of steps here will be, it should be equals to n1 plus n2 plus 1, which should be equals to moves n minus 1 S A D plus 1 plus moves n minus 1 A D and S. Now using this logic, we can go and write the recursive function. Let's try to go and write it. So if I go and open my code, right, let's go and create another file. Let me go and create a file called as file, save as, and let me go and call it as tower of hanoi.js. So in that sense, let me go and define a function called as function moves, and we'll take the input, which is the number of coins, then the source, then destination, and then auxiliary. Now if it is a recursive function, I have to go and write what? I have to write the base condition. So I know the base condition. If there is only one coin, so I know the base condition. What is the base condition? The base condition says that if n value is equals to 1, then go and return 1. Perfect. If n value is equals to 1, then simply go and return 1. Else, what you go and do is, you first move n minus 1 coins. You move n minus 1 coins from source to auxiliary using destination. Then you move one largest coin to the destination one in the one steps, and then you again move n minus 1 coin from auxiliary to destination using the source. And this what you get, you should go and return it. Fair enough. Let's try to see if this works. What I want to do is that let me go and write some test cases. I go and write console.log, and I'll go and put as moves, and I go and set that 1 source, destination, auxiliary. We copy more, move 1, I go and put 2, I go and put 3, I go and put 4. If I go and run all of them, right, if I go and say the node QH.js, I see here for 1 it is giving me 1, when it is 2 it is 3, when it is 3 then it is 7, when it is 4 it is 15, right? So I'm able to get the answer. And if you try to find some kind of correlation here, we're going to open my scribble. If it is 1, then it is 1. When there are 2 coins, it takes me 3. See the beauty of maths here. If it is 3, I'm getting 7. So if you see here and try to find the pattern, can I say that the value should be equals to 2 to the power n minus 1? Because when n is equals to 1, this value is 1 minus 1 equals to 1. When n value is equals to 2, this value is 2 to the power 2 minus 1, which is equals to 3. When n is equals to 3, this value is 2 to the power 3 minus 1 is equals to 7. Right? So mathematically, I can go and find the answer to be 2 to the power n minus 1, where n is the number of the coins. And this is how we go and solve the tower of hanoi. Now what I want you people to do is pause this video, go and watch it again if you have not been able to solve it. And once you have solved it, try to dry run this code, boss. Please dry run this one because it will help you get things better. So now since we have understood tower of hanoi, now what we'll do is we'll try to solve few good level questions, medium level questions, lead code questions, and let's try to solve on the lead code itself to master recursion. Let's get started. Now let's get started with the first problem from the lead code, right? So this is a lead code problem which you see on the screen. If you have to go and find over the lead code, just do a quick search, right? You can just go onto the Google and search lead code followed by this 46 permutations, and will direct you to the direct link of this problem statement. I'm assuming that you'll be able to do this basic navigation and go to the lead code and solve this problem. Now this question is of the medium level difficulty. Every question on the lead code that you do is tagged to a difficulty level of easy, medium or hard. It has been asked in the different companies. Now this question is trying to say that you have been given an array, right? You are given an array of distinct integers, right? So the array of integers are there and all the number has to be different. Return all the possible permutations. You can return the answer in any order. So for example, in this case, if it is 1, 2, 3, it is saying that 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. These are the number of permutations. Now, if I go and talk about the basic maths, if there are n digits and they're all different, so number of permutations will be equals to how much? N factorial. Right? So for example, in this case it is 3, so it is 3 factorial. So it is 3 into 2 equals to 6, and if you can see here the 6, 1, 2, 3, 4, 5, 6. Here it is 2 elements, so 2 factorial value is 2 equals to 0, 1 and 1, 0. Here it is 1 factorial which is equals to 1, so you only have one value. Fair? Does it make sense? So now we have been given an array of distinct integers. What I have to do is that I have to go and find all the possible permutations of the given array. Now let's try to think that how we can go and solve this problem. Let's say that initially I have been given an array called as 1, 2, 3. Now in order to solve this problem, what I can do is that I can actually replace elements, right? I can go and swap 1 and 2. So this can give me one combination called as 2, 1 and 3. Another could be, say for example, I go and swap 2 and 3 positions. So this could be a position called as 1, 3, 2. So basically we have to find all the possible arrangements made by swapping the elements each other out. And when we go and find all those options, I'll get all the permutations itself. But can we try to do this little logically? Right? So to do things little logically, if I think little more logically, what we can do is that out of 1, 2, 3, first what we can do is that we can fix the position at the first position of 1, right? So one position is fixed right now, and then I can either put 2 before 3 or I can go and put 3 before 2. The another strategy is that now the second digit is fixed. Now I can put 1, 3 or I can go and put 3, 1. The third step, I go and fix the 3, I go and put 1, 2 or I can go and put 2, 1. When I go and put all these 3 together, these are the 6 permutations. Fair? So for this question, if I have to go and solve it logically using, let's say that what is happening here, once you have fixed this, right? Initially it was a problem size of 3, now it is a problem size of problem 2, and a repeating pattern. So typically this problem could be solved using the recursion. So how can I go and solve using the recursion? So let's say that if it is 1, 2, 3. Now at this point I'm focusing around this position. So this element has to be swept by either this or this or this, right? So if that happens, there are 3 possibilities. One is swept by 1 itself, so it becomes 1, 2, 3. Second possibility, 1 is swept by 2, so it becomes 2, 1, 3. And third possibility is that it is swept by 3, 3, 2 and the 1. Now in this case, first thing is done. Here also second is done. Here third is done. Now what I need to do, I need to go and compare 2 and 3 stuff, right? So now 2 and 3, so this becomes, when the 2 is replaced by the 2, so it becomes 2, 3. When 2 is replaced or swapped with 3, it becomes 1, 3, 2. Same way here, when 1, this middle one, 2 remains as it is, 1, 3. Or I can go and write as 2. I can go and write it as 2, 3, 1. Here I can keep 3 fixed, 3, 2, 1. And then it should be 3, 1 and 2. And what you see at the leaf of this recursion tree, these are the possible 6 combinations. So if you try to go and decipher the logic here, what the logic that I'm trying to apply? The logic I'm trying to apply is that I have to, in a given array, at any position I have to go and swap these 2 elements. Swap 2 elements. And in this swapping, I have to follow all the possible permutations and combination. If I go and follow all the possible permutation and combination, I'll be able to go and find all the possible permutations of the given element array. Let's try to write the logic for this directly on the lead code, and we'll do again the dry run and dry code of that, right? So let me go and quickly open my Chrome, and you can see the screen is already here, right? This is the link, lead code permutation 46 permutation itself, right? There will be multiple languages in which you can go and write the code. I'm going to make use of JavaScript itself, right? There's already a permute function written here. What I have to do is that I have to return the array of arrays. So first of all, let me go and define something called as let resource response. Let me do one thing. Let me go and copy this on my code so that my indentation could be all well. So let me go and open on my code, and here let's try to write this code itself, and then I'll paste it from here to that position. Let response. Now what I can go and say that if you see here, when I was solving, first 1 was replaced by 1, and then typically 2 was replaced by 2 and 3 was replaced by 2, right? So once I'm done with this, I always have to go back and then again start doing it, come down, again I have to go back, then I come here, then again go back. So typically the same array has to be modified multiple times, right? So this whole concept of solving the problem like this, in which you always have to go back, is called as backtracking. Now instead of talking too much of theory around what backtracking is, what not, let's try to solve the problem directly and then see that how the backtracking is being utilized in this problem itself. So again I go back to my code, and I'm going to define a function called as function backtracking. So let's start backtracking, right? So we'll start with the first index. Let me go and call it as backtrack from the start. And then what we do is that, let me go and do the condition. If I go and say that start value is equals to nums dot length, in that case what should I do? I should go and say that rest dot push, and just hold on, let me complete the code, try to follow along, and then we'll have a discussion on that what we did. And then I go and do this nums. What is the meaning here? This means, if you try to see the code here, this means that I'm trying to the cloned copy of array, because we are doing the backtracking, we are changing the same array, so we are storing the clone copy of the array itself. Okay, now let me make this screen size a little bigger. If that is not the case, then what I do, I go and write the loop for let I is equals to start, I is less than nums dot length, I plus plus. And then what I do, I go and swap the element at the ith index and the start index. So I go and say that let temp equals to nums start, and then I go into the nums start equals to nums number I, and then I go and do this as num I equals to temp. Fair enough. And once that is done, typically what I'll have to do is I'll have to go and call this function again inside this, right? So what I go and do is that for this for loop, every time I go and do this, I'll go and call this function recursively backtracking, and I go and say that start plus 1, and then I again go and repeat the same thing. I undo this thing. Right, so I go and do the reset the array, right? Once everything is done, typically what I go need to do is that I have to go and call this function backtracking 0. Backtracking, I go and pass 0, and typically I go and return this result that I created. Now let me go and copy this code and run it on the lead code and see it works, and then we'll try to review the code that how did it. So I'm going to paste this code here inside this. We go and paste this. Perfect. So this code has been pasted. Just need to run this and see if it works. And if you see here, all my 3 cases have been running perfectly fine. If I go and click on the submit, let's see the submission status. So the code has been submitted, and my code has beaten 93.77% of the submission. Perfectly fine. Now I go back. Let me take this code now out from here, and let's try to understand that what we have written, right? Let's copy this up. So if I go back to my open board, right, and paste the code here, let's try to understand what we did, right? So let's say that I went ahead and called a function call as a let me go and call this function permute as permute, and inside this I go and passed 1, 2, and 3, right? I know that I have to go and create a recursive tree like this, 1, 2, 3, and then we have already seen this recursion tree here itself, right? This is the recursive tree. Now let's try to see that how this code executes. So what I did is I initially defined this response array, in which, because I have to go and return the results, then I define this function called as backtracking, and I call this function backtracking at the 0th. So what happens at the very beginning itself? 1, 2, 3. Start value is equals to 0. Numbers dot length is equals to 3. It doesn't go inside this, so it comes here. And when it comes here, you start with 0, and the very beginning I value is equals to 0, and start value is also equals to 0. So if you try to see here, what I'm trying to do is that I'm trying to swap 1 with 1. So the result is 1, 2, 3 itself. Once it is done, I move to the next step. I'm trying to swap 2 with 2, and the result is itself. And I'm trying to swap 3 with 3, and the result is itself. And then since there's no more recursive call, I swap back 3 and 3. So if you see here, I'm going down, and then I'm coming back, again going down, and again coming back. So this whole code which you are seeing on the screen is an example of backtracking, and using the backtracking we are trying to solve this problem. I hope you are able to make sense of this question. It's a medium labeled question. It might be little tricky to start with. I'll suggest you people to, if you have not made it in the first go, pause the video, give it a thought, think over it, but don't try to copy or mug up the solution. That's not the whole key, right? This is a recursive question. It takes some time. It takes your brain to think for a while and then get ready for this kind of solutions. So don't worry much on that. Spend some time, try to solve this question, and then we'll try to move on. We'll try to keep this video here itself. I understand this could be a little overwhelming, so I'll just keep the video here itself, but we'll solve more problems in the coming videos. Just spend some time here, set your mind ready for the more problems, and in the next session we'll solve multiple problems of the permutations. Multiple problems of not permutations but recursions. Thank you. Thanks for watching.